Good morning everyone. Myself, I'm G. Likhta from CSIT. Today's my topic is matrices as transformation. Let's start with the introduction to linear transformations. Function T that maps a vector space V into a vector space W, that is T mapping V to W. V comma W tends to vector space. Here V is the domain of T and W is the codomain of T. Here is the diagram for the given mapping. Image of V and a T. If V is in V and W is in W such that T of V equals to W, then W is called the image of V and a T. The range of T, the set of all images of vectors in V. The pre-image of W, the set of all V in V such that T of V equals to W. A function, one of the example is a function from R square into R square. T mapping of R square to R square. V equals to V1 comma V2 that belongs to R square. T of V1 comma V2 equals to V1 minus V2 comma V1 plus 2V2. Find the image of V equals to minus 1 comma 2 and find the pre-image of W equals to minus 1 comma 11. First one, V equals to minus 1 comma 2, T of V equals to T of minus 1 comma 2 equals to minus 1 minus 2 comma minus 1 plus 2 of 2 equals to minus 3 comma 3. T of V equals to W equals to minus 1 comma 11. T of V1 comma V2 equals to V1 minus V2 comma V1 plus 2V2 equals to minus 1 comma 11. V1 minus V2 equals to minus 1, V1 plus 2V2 equals to 11. V1 3 and V2 is 4. Thus 3 comma 4 is the pre-image of W. Next, linear transformation. V comma W is in vector space. T mapping V to W, that is V to W linear transformation. T of U plus V equals to T of U plus T of V, that is U comma V belongs to W. T of CU, that is constant into U equals to constant into T of U. This is the formula. And here C belongs to the real number. Notes, a linear transformation is said to be an operation preserving T of U plus V equals to T of U plus T of V. T of constant into U equals to constant into T of U. This is addition in V and this is addition in W. This is a scalar multiplication in V and this scalar multiplication in W. A linear transformation T mapping V to V from a vector space into itself is called a linear operator. Verifying a linear transformation T from R square into R square, and the example is T of V1 comma V2 equals to V1 minus V2 comma V1 plus 2V1. U equals to U1 comma U2, V equals to U1 comma V2 vector in R square. C any real number vector addition U plus V equals to U1 comma U2 plus V1 comma V2 equals to U1 plus V1 V2 plus V2. T of U plus V equals to, if we solve this equation we get T of U plus T of V. Scalar multiplication, constant into U equals to constant of U1 comma U2 equals to CU1 plus CU2. Here is the proof for the scalar multiplication, and therefore T is a linear transformation. Functions that are not linear transformations. F of x equals to sin x. Sin of x1 plus x2 is not equal to sin of x1 plus sin of x2. Sin pi by 2 plus pi by 3 is not equals to sin pi by 2 plus sin pi by 3. These are not linear transformations. Here f of x equals to sin x is not a linear transformation. And f of x equals to x square, x1 plus x2 whole square equals to x1 square plus x2 square is not equal, and 1 plus 2 whole square is not equal to 1 square plus 2 square, and so f of x equals to x square is not a linear transformation. And f of x equals to x plus 1, f of x1 plus x2 equals to x1 plus x2 plus 1, f of x1 plus f of x2 equals to x1 plus 1 plus x2 plus 1 equals to x1 plus x2 plus 2. F of x1 plus x2 is not equal to f of x1 plus f of x2. So f of x equals to x plus 1 is not a linear transformation. Notes, two uses of the term linear. F of x equals to x plus 1 is called a linear function because its graph is a line. F of x equals to x plus 1 is not a linear transformation from a vector space R into R because it preserves neither vector addition nor scalar multiplication. Zero transformation. T mapping V to W. T of V equals to 0 and V belongs to V. Identity transformation. T mapping V to V. T of V equals to V and V belongs to capital V. Theorem. The first theorem of properties of linear transformation is T mapping V to W and U comma V belongs to V such that the first condition is T of 0 equals to 0 and the second condition is T of minus V equals to minus T of V. The third condition is T of u minus v equals to T of u minus T of v. If v equals to c1, v1 plus c2, v2 plus so on, cn plus vn, then T of v equals to T of c1, v1 plus c2, v2, so on, cn, vn. Here c1 T of v1 plus c2 T of v2, so such that cn T of vn. And the example of linear transformations and bases. Let T mapping to R cube tends to R cube be a linear transformation such that T of 1, 0, 0 equals to 2 of 1, minus 1, 4, T of 0, 1, 0 equals to 1, 5, minus 2, T of 0, 0, 1 equals to 0, 3, 1. Then find T of 2, 3, minus 2. Here we can get this by multiplying in the given form, so that the given points are 7, 7, 0 as we solve as shown in the PPT. Let's see the second theorem of the linear transformation given by a matrix. Let A be an m into n matrix. The function t defined as T of v equals to A into v is a linear transformation from R power n into R power m. Here the note is AV equals to, as in given pattern, into V, then converts into the given matrix. Here this is Rn vector and this is Rm vector. T of V equals to A into V. T mapping R power n tends to R power m. Example, next example is rotation in the plane. Show that the T mapping R square tends to R square given by the matrix A equals to cos theta minus sin theta cos theta has the property that it rotates every vector in R square counterclockwise about the origin through the angle theta. Here is the proof to show it. T of V equals to A into V. We can solve the matrix as given. We can multiply it. And here R is the length of T of V and theta plus alpha is the angle between the positive x-axis counterclockwise to the vector T of V. Thus T of V is a vector that results from rotating into counterclockwise through the angle theta. Example 8. A projection in R cube. The linear transformation T mapping R cube to R cube is given by given matrix is called a projection in R cube, and the diagram is given for it. Example 9. The linear transformation from m cross n into n cross m T of A equals to A power transpose T mapping mn tends to mnm. Show that T is a linear transformation. Here is the proof to show that T is a linear transformation. Matrices for linear transformations. Two representations of the linear transformation T mapping R cube to the R cube. The first condition is T of x1, x2, x3 equals to 2x1 plus x2 minus x3 minus x1 plus 3x2 minus 2x3, 3x2 plus 4x3. T of x equals to A into x. Three reasons for matrix representation of a linear transformation. The first is it is simpler to write and it is simpler to read. It is more easily adapted for computer use. Next theorem. Standard matrix for a linear transformation. Let T mapping R power n tends to R power m be a linear transformation such that then the m cross n matrix whose n columns corresponding to T of e power I is given is such that T of V equals to AV for every V in R power n. A is called the standard matrix for T. Here is the proof for it. Let's see about inverse linear transformation. If T1 mapping Rn tends to Rn and T2 mapping Rn tends to Rn are such that for every V in R power n, T2 of T1 of V equals to V and T1 of T2 of V equals to V, then T2 is called the inverse of T1 and T1 is to be invertible. Note, if the transformation T is invertible, then the inverse is unique and denoted by T inverse. Let's see about the similarity. Example for similar matrices are if A equals to 2, minus 2, minus 1, 3 and A transpose equals to 3, minus 2, minus 1, 2 are similar because A transpose equals to P inverse into A into P where P equals to 1, 1, 0, 1. Next, A equals to minus 2, 7, minus 3, 7 and A transpose equals to 2, 1, minus 1, 3 are similar because A transpose equals to P inverse into A into P where P equals to 3, minus 2, 2, minus 1. Let's see the note. Computational advantages of diagonal matrices. Here the diagonal matrix is given in terms of K and normal diagonal matrix. Here D transpose equals to D is the second condition, and the third one is D inverse equals to given matrix. Here Di is not equals to 0, means the diagonal element should not be 0. Thank you.